So as I said, if we get through today, so we're up to lecture 19. If we get through today, we're in pretty good shape, particularly because Monday is a public holiday, as a holiday for us. So we'll be missing that lecture anyway. So even with that, we'll be finished, I think, well and truly into week. We'll be well and truly finished, more or less at the beginning of week 11, I think, which is pretty good. Okay. The other thing to remember too is, as I'm going along, just like if this was in a classroom, if something goes astray or you don't understand something, please chime in and ask, or tell me if my writing's gone off the page. Part of my problem is that my screen is not in front of the document camera, so I'm not always aware of where I'm actually writing. Most of the time it's okay, but sometimes when I get a bit carried away. Right, so in this lecture, we're going to do, we're going to also look at another sort of search called a binary search. This is kind of what you might do when you're looking up, for those of you who remember telephone books, what you might do when you were looking up a telephone book in the old days. So let's see how that works. But a few things that we need to look at just beforehand. So again, we'll okay, I think it looks reasonable. Right, principles of big O notation. So, look, I have to say this is a flying introduction to this big O notation. On my bookshelf at work, I brought it with me. I've got a book that's about, let's see, not this one, but it's about yay thick. It's just about complexity of. Let me do it this way. All right, so I've got a book on my shelf, not this one, but something comparably as big, and it's just about complexity of algorithms, how you count the number of operations. So in a sense, this is, if you like, a whole subject in its own right. But the main idea with you is that we're just skimming over the surface to give you a flavor of what exists out there. So you could literally have a whole subject just on sorting and searching algorithms, so sorting and searching. You could have a whole subject on complexity, how many operations algorithms take in general. So we really are just skimming the surface, but as I said, the idea is just to at least let you be aware that these things exist, rather than get you up to speed in applying them, if you like, in real life. Just need to be aware that they're there, at least have a basic understanding of the terminology. So going back to this, so our big O notation. In the last hour, what did we do? Okay, so the important thing for us is that if you say big O n squared, or order of n squared, we say, it takes roughly n squared. So it could be 100 times n squared, or it could be 3 times n squared. It's just something times n squared, where n is the size of the input. So with 10 inputs, it performs approximately 100 operations. In a sense, we don't care if it's 100 or 900. It's some multiple of 100. But we do worry about it if it's 1,000 or or 10,000. So there are some rules about how this big O notation works. And I started to talk about operations. So when we were adding numbers, the operations that we were counting were the actual additions. When we're doing the sorting, the operations were the comparisons. Turns out that in computing, at least in the old days, a comparison was about equal to a multiplication. And it turned out that additions were very, very cheap to do. So you could do lots and lots and lots and lots of additions for the cost of one multiplication. So in a sense, when you're analyzing big numerical algorithms, what you're really interested in is the number of multiplications and divisions and comparisons, and you're almost not worried about the actual number of additions that are involved, because they're usually much cheaper. They're easier to do the wiring in the chips that do this stuff. The thing that I did gloss over with the sorting is that, yes, we are comparing one entry with another entry, but there's also a cost involved in moving stuff around. So, I was quite blithe in this. Where's my... Where's my thing? So going back here, to go from this, at this stage, this is step 4 of this particular list of the insertion sort. Okay, we had to make comparison, 1, 2, 3, 4, 5 comparisons. But the thing that we didn't count, and we're sort of not going to, but it is important, is that if you're programming this, there's a cost involved in taking this element and putting it there, so assigning it. So you either have to, if these things are actually in the list, you actually have to shift things up or shift things around to be able to say that 2 fits in there. There are shortcut ways. I think there are things called pointers and indices, which can be used. But if you think about sorting a deck of cards, you do a comparison, but you also actually have to take physically a card and put it somewhere in the list. And that physical allocation has to be done in the computer as well. And so there's also a cost involved. So that's what this is really saying, that shifting data around is costly. A long time ago, when I lived in America, the place that I was working at had a big, one of the early supercomputers, and I mean, it was just a ginormous thing, but it was a ginormous thing, and the big thing with it was not so much the computations that had to be done. So they were looking at, one of the things that they were looking at was modeling airflow over airplane wings, that sort of thing, airflow over objects, numerical simulations using these powerful supercomputer with some very sophisticated algorithms. The big cost was not the algorithm itself, but was moving data around within the computer. And it's a big field. Just how do you minimize the transfer of data from one location to another? Because in a sense, it's the transfer of data which causes a lot of heat generation in the hardware. So keeping these supercomputers cool is a big issue. So so it's not just the time complexity, but it's also the physical maintenance of the computer as it's computing, as it's doing calculations. It's doing operations, but it's also physically shifting around data within, and that, as I said, generates a lot of heat. So it was pretty impressive to see for me back then. So as I said, that's what's happening here. It's not just the arithmetic operations or the logical comparisons, it's actually shifting stuff around. Yeah, assignments are pretty fast, depending on, but if you've got a lot of them, it can slow things up, and often that is, in fact, is the bottleneck. Multiplication divisions are usually the slowest things of all. Even to do multiplication and division, I mean, you have two numbers that you want to multiply. Well, what happens is that they actually have to be transferred into something. Then there's the multiplication has to happen, and then the output has to be transferred to somewhere else. So there's actually a lot more involved than just doing the multiplication. So, but as a general principle, let's ignore physically moving stuff around. Let's just concentrate on what are the most expensive things. And by and large, what we do is, if we've got arithmetic operations, then usually we just count the multiplies and divides together with the comparisons. So the first rule is you only count what is the most time-consuming stuff. So this whole idea about the order of this big O notation is it's just trying to extract roughly how big things are. So, as I said, we don't really care if it's 235 or 232 steps. We say it's about 100. We don't care if it's 42,000 versus 57,000. It's about 10,000 is roughly the what we're thinking of. So if we've got 4 additions and 3 multiplies, we really are not worried about the additions. They're just so blindingly quick compared to multiplication. So we'll just count those. The second rule is what we basically did with our first example of sorting. Here was an initial list of numbers, and it took, for this particular list, 23. On the other hand, we saw if the numbers were already in order, it would only take 7 operations. But if the list was really jumbled up, or actually it's not really even jumbled up, but if it's in the wrong order, in the reverse order, it actually takes the greatest number of operations, the worst case. So what we do is, just like we only interested in what are the most expensive operations, we'll also only be interested in what's the worst thing that can happen. So that's really rule number 2. The computation time could vary depending on the particular input. What we're interested in is what's the worst that can happen. So with our sorting, the insertion sort, the worst that could happen is that we need half times n minus 1 operations, which are comparisons in that particular case. Even though a list that's already sorted only takes n minus 1 comparisons, a list that isn't sorted might take that many. Rule number 3. We really don't care about small inputs. When we did the example about sorting a list with just 8 elements in it, 8 is really small. In a sense, that was just a toy problem to help us understand the bigger problem. What we're really interested in is what happens when the input size is large, because that's going to take the large amounts of time or the large number of operations. So if the size of the problem that you're putting in is small, basically all algorithms are going to be pretty quick. It's like saying if you've got a list of 10 numbers or a list of 10 names, almost every algorithm that you implement will take about as long as each other, because 10 is not very many. I mean, if I asked you as a human, here are a list of 10 names, you will do it pretty quickly just by looking at it. But if I gave you a list of 1,000 names, it's going to take you a lot longer. And that's what we're doing with the computer. We're asking what happens in the worst case, but also what happens in the case of large input sizes. So we're basically going to assume that the number of inputs is large. Fourth rule. I mentioned this a couple of times. We can write out a formula for the exact number of operations in an algorithm. So for insertion sort, the exact number is a half n squared minus a half n. So if I know the size of the input n, I know exactly how many comparisons is going to be in the worst case. So half n squared minus a half n. This fourth rule says that when n is very big, let's say even 100, a half n is a half times 100, but a half n squared is a half of 100 squared, which is 10,000. Now, I don't really care. I mean, if it's going to take 10,000 steps, I don't really care if I can save 100. It's not going to make a lot of difference. I mean, think about this in seconds. If this is going to take 10,000 seconds to work, another 100 seconds here or there isn't going to make any difference. If this is 10,000 days, another 10 days, another 100 days is not going to make any difference, really. So instead of being exact, I say, well, I don't really care about that because that doesn't contribute very much when n is very large. The thing that's contributing is the half n squared. And in fact, in a sense, I don't really care about whether it's a half of 10,000 or exactly 10,000. So I'll even ignore the half that's sitting in front of the n squared. That's what's going on here. We're only considering the dominant term. So the dominant term in this particular case is the half n squared. So this is why we'd say that this is order, and we don't even care about the half. This is order n squared. So it's about, if I know that the input is going to be 100, then 100 squared is 10,000. So I know it's going to be somewhere around 10,000 steps. Could be a bit less, could be a bit more. I don't really care. It's just about 10,000. So if you know that it takes exactly n cubed plus 2n squared, the thing that's really important in counting the steps is the n cubed. So that's why we say this is order n cubed. N squared plus 2n, what order is it? Well, it's order n squared in exactly the same reasoning. Oh, sorry, no, my mistake, I didn't read this right. N squared plus 2 to the n. What's the time complexity of that? So sorry about that, I didn't read it properly. I thought it was saying 2 times n, not 2 to the n. Okay, so if n is big, out of n squared and 2 to the n, which one is going to be bigger? And you say to yourself, well, that's a exponential growth, 2 to the n. This is a power, and exponentials always beat powers. So this is going to be order 2 to the n, because it's going to be dominating. Actually, if I do this, let's see if I can start it up. Just bear with me for a tick. See if I can fire up this again. I'm just firing up Maple because I want to show you. Oh, it's not working. Nope, it's not going to do that for me. Oh, I see what's happened. Just bear with me for 1 minute. All right. Okay, so here's Maple. We did a little bit of this the other day. Computer algebra package. Now, if I say what we were looking at, n squared versus n to the 2. So if I take 100 and I square it, okay, well, I get I would get if it technology today. No, it's not responding. I'll just try that again because I think it's worthwhile having a look. Just bear with me I'll bear with my computer another 30 seconds. All right. Ah, good. Okay, I can share it with you. Right. So you should see my maple screen. So I just calculated 100 squared. Yeah, you can do that in your head. That's 10,000. Now, let's compare 2 to the power of 100. So remember, we've got n squared versus 2 to the n. So what's 2 to the 100? Yeah. So if it's going to take this many seconds, and I'm going to add another 10,000 seconds, which one is bigger? I mean, which one dominates? Well, clearly the 2 to the 100 will dominate, and I really don't care about the 100 squared operations. It's trivial in comparison. So that's what we mean about the difference between an exponential versus. Can you see my cursor moving? Okay, Dale's shaking his head. Let's see if I can do annotate. Right. Yeah. So here's my exponential. Here's my power. Which one is bigger? Even for a small input size like 100, well, the exponential is way, way dominating. So basically, we can ignore that bit and say, if I've got that plus that it's almost equal to 2 to the 100. So that's what's going on. I'll tell you the other thing that's happening with me is that I've got 2 screens, one on the right of the other. But when I take my cursor off to the left of one, it doesn't go to the other one. It actually, where's my cursor gone? My screen's the wrong way around. Okay, so that's what's going on here. You've got n squared plus 2 to the n. 100 squared versus 2 to the 100. Which one dominates? The 2 to the n. That's why we just write it like that. The other one is, we've really kind of covered it. Half n squared versus n squared versus 10n squared. Yeah. They're all just multiples of n squared. So I don't care about the multiple. I'm just interested in what's the main term. So this big O notation just gives us a quick way to compare magnitudes. So if you've got a choice between an order n to the 7 and an order 2 to the n algorithm, which one would you choose? Well, the one that takes a fewer steps with large input, basically that one, because this is just going to take too long. So insertion sort, it requires exactly half n times n minus 1 step comparisons. A half n times n minus 1 is a half n squared minus a half n. What's the dominant term? The half n squared. That's one of our rules. We ignore the half, so this is why we say this is actually order n squared. It's just an easy way then of comparing. Like this, we can compare complexity of one algorithm with another, just very roughly. Okay, so binary search is just another kind of obvious way of doing searching. Okay, so searching and sorting are two of the most common things that we need to do in computing. So what we're going to do is look at time complexity of this binary search. Again, there are different ways of searching through all this. So in this case, we're not trying to sort it, but we're looking for something in it. So we're looking for a particular value that's already in a list that is already sorted in some fashion. So suppose we're looking for 55. Where is 55? Now, as a human, you kind of just look at that and you see straight away where it is. But computers are really dumb, and you've got to tell them explicitly what to do. So what's the obvious thing to do? Well, you say, I'm looking for 55, so I'll just start at the beginning. So is that 55? No. Is that 55? No. Is that 55? No. Is that 55? No. You keep on looking until you get to 55. You just hope that you weren't looking for the one that's at the end of the list. So that would be a really obvious way of searching through it. Just start at the beginning and work your way forward. But it's not really the most efficient. At worst, it will take as many steps as there are things in the list. So a different way is what's called a binary search, or sometimes called a divide and conquer algorithm. And basically what you do is you divide the list into two pieces, so a left half and a right half. And you decide, is 55 in the left half or the right half? And the way you do that is by comparison. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers, 11 things in the list, 11 elements. The middle one is going to be the sixth. So 1, 2, 3, 4, 5, 6. So here's the middle one. And you simply look at the middle one and you ask yourself, where is 55 in comparison to 41? Okay, so 41 is less than 55, or better still, 55 is bigger than 41. So you know, without testing all these guys, that 55 is in this part of the list. So you've already saved yourself 1, 2, 3, 4, 5 comparisons just by looking at the middle one. So now we know that, so that's just one comparison to decide that 55 is in the right-hand half. And now you do the same thing again. So this is element 1, 2, 3, 4, 5, 6, 7. So this is element 7, 8, 9, 10, 11. We know that 55 is bigger than that. So basically, we know it's on that side. And we do the same thing again. Right? We've basically eliminated that lot. Now we've got to look for 55 in that really short list. So let's do the binary. Binary just means split into two in this particular case, or why it's sometimes called divide and conquer. So what's the middle number of this list? Well, it's now 72. So you ask yourself, 55 is less than 72, or better still, 72 is not less than the target of 55. So you now know that it's in this part of the list. So we've made one comparison to decide it's in the right-hand half. Then within the right-hand half, we've made another comparison to decide that it's in the left-hand half of this shorter list. Okay. So you know that, oh, sorry, my mistake. Put my dividing line in the wrong spot. Okay. Should put it there. Okay, I'm putting the dividing line there because of this sentence. 72 is not less than the target. So 72 is not less, so you know it's 55 is in here somewhere. So 55 is either that one, or that one. So between elements 7 to 9. Okay, well that was one comparison to make that. Okay, so where are we up to? Okay, we divided it there. We divided it there. Okay, that was two comparisons so far. Now we compare 55 to the middle number of this. smaller list. Notice that we're effectively halving the size of the list at each step. So 68 is not less than 55. Think about it as bigger than. So the target 55 is either this one or this one. Okay, so that was, so now there was another comparison with 68. So the target's somewhere between this one and this one. Okay, 55 is not less than the target of 55. So it can't be to the left of that. So we've decided this is where it is. So basically we've made 4 comparisons. So we've compared, and the comparisons are less than. Is this less than that? No, so it's over here. Is this less than that? No, so it's in here. Is this less than that? Yes, it is, so it's in there. Is this less than that? No, it isn't. It's not strictly less, it's equal to that. So we've zoomed in on where it is. The really important thing is that basically we've halved the size of the list at each step. So, so if you had a list of 32 things, then the right hand or the left half, or left-hand half would be size 16. And then you've got to figure out where your target is in that smaller list. So you divide it in 2 again. Then you decide which half of it's in. It's 4, 2, and eventually 1. So you actually, and halving the list at each step is really just one comparison. So if you've got 32 things, you've effectively got 1, 2, 3, 4, 5, 6 comparisons to make. So that's a specific example, but go back to our general principle. What's the worst thing that could happen if you had 11 numbers? The worst thing that can happen is that if we think about comparing using the less than, and there's an even number of entries, then we should just compare to the left of the middle. I'm going to truncate this. So what's the worst thing with 11 numbers? The worst thing with 11 numbers is that you'll have 4 comparisons. Yeah, okay. If you've got 15 numbers, what's the worst thing that can happen? Okay. Well, 15 is an odd number. So if you've got 15 things and you divide them into 2 lists, they're not going to be equal halves. You're going to have 8 in one and 7 in the other. So that's the most, well, that's the closest to an equal division. And if you're unfortunate enough that your target is in there, that's going to take a little bit more work than if it was in here, because there are just fewer things. So that's why I'm saying if you've got 15 in the original list, then you divide it in 2. Well, the worst thing that can happen is that your target is in the slightly longer half. Then when you divide that into 2, it's in so there are your 8 things. If you divide it in 2 again, you know, it could be in this half. So you've only got 4 things to check. Then if you divide in 2 again, it'll be in that half. And then you divide it in 2 again, it'll be in one of the other halves. So 1, 2, 3, 4 comparisons. You've got 16, okay, 16 things, and you divide your list into 2, you'll have 8 on one side and 8 on the other side, and you keep on dividing in half. So again, you only need 4 comparisons. What if you had 17? Okay, well, you can't divide it exactly in half. The worst thing that would happen is that you would have 9 in one half and 8 in the other half. Okay. And then if you're unlucky enough that your target's in there, then you might have 5 in that half and 4 in that half. Then if you're unlucky enough that it's in here, you'd have 3 in that half and 2 in that half. And if you're unlucky enough for it to be in there, you'd have 2 in that one and 1 in that one. And if you're unlucky enough for it to be in there, you'd have 1 and 1. So if you're really unlucky, your target is always in the slightly longer half, in which case you'd actually need 1, 2, 3, 4, 5 comparisons rather than 4. Now, I won't go through all the details of it, but you could check this for yourself. If the size of your list is anything from 9 to 16 names or numbers, you'd need at most 4. From 17 to 32, you only need 1 more comparison. So if you double the size of the list, you only actually need 1 more comparison, effectively. If your size of the list is 33 to 64, the worst that will happen is you need 6. So if you go from 32 to 64 names, and you're looking for a name in them, you only need actually 1 more comparison. Because you're not comparing with everything. You're just comparing with the middle one, and that takes care of a whole lot of things. So you can see that's a pattern here. These are basically powers of 2. So this is 2 to the power of 4. This is 2 to the power of 5. This is 2 to the power of 6. So basically, if your input is more than 2 to the 3 and less than 2 to the 4, what's the most you need? 4 comparisons. If your input is bigger than 2 to the 5 or bigger than 33, but not more than 2 to the 6 at 64, you only need 6 comparisons. So we've got this thing that if your list is between 2 to the n minus 1 and 2 to the n in size, let's use another one. Using n in different ways here. 2 to the k, that's one. So if your n is between, if your n is between 2 powers of k, the number of steps or number of comparisons is the k, which is basically log base 2 of your n. So if your n is anywhere between 2 powers of 2, then the greatest number of comparisons is that exponential of 2, so 2 to the 6 here. That'd be k steps, and 6 is the logarithm base 2 of 64. So basically, you're looking at effectively log base 2. So what's good about log? It grows really, really slowly. So you double the number of things in your list, you only need 1 more comparison. Now, 128 only needs 7 comparisons. 1024 only needs 10 comparisons. That's pretty amazing. If you've got a list of 1024, you only need to do 10 things to find an element in the list, which is really what this is saying. If you've got 1,000,000 things, which is 2 to the 20, what's the worst case? You need 20 comparisons. Okay, now something slightly different. Just take a couple of minutes for this. Suppose I ask you to guess a credit card number So the idea of this is we're going to, it's a FOIL, a comparison against searching within a list. If I ask you, just guess the credit card number. Now, credit card number has usually 16 digits, so 4 groups of 4, I think. If you had to guess it, or guess a PIN number, think about guessing a PIN number. If you've got a 2-digit PIN number, how would you go about guessing it? Well, sort of an obvious thing would be you just start with 00 and you try everything up to 99. So you'd have basically 10 squared possibilities that you have to look at. If your PIN number was 4 digits, or your credit card number was 4 digits, let's suppose it's a little credit card, but if it's a 4-digit PIN number, what are the possibilities? Anything from 0000 up to 9999, which if you had to try every one in turn, the worst thing that would happen is 10 to the 4 operations, or 10 to the 4 guesses before you found the right one. And this is the whole point about cryptography, is that you want to make it difficult for somebody to go through every possible key or every possible, if you like, password. What's the worst case if you've got n digits? It's 10 to the n possibilities, or 10 to the n operations, which is exponential, which means that it's just going to take you a long time to try and guess something, unless you're really lucky, but you never know that you're going to be. Which is why passwords, they ask you now to have lowercase, uppercase, numerals, and preferably, so lowercase, uppercase, numerals, and preferably non-numeric characters as well. And if you've got a mix of those, there's just a huge, so there's 26 of those, 26 of those, 10 of those. I think there's about 10 of those. So 52, 60, so altogether, there are about 72 different things. And if you've got a password with 8 characters, then there are 72 to the 8 possibilities, which is a pretty big number to guess. So if I ask you, credit card numbers are 16 digits, and if I ask you to guess what a credit card number is, simply by starting at 0000 and working your way all the way up to 999999999 by trial and error, and you could do a million guesses a second, how long would it take? Well, there are 10 to the 16 possibilities. You could do 10 to the 6 possibilities per second. That's 10 to the 10 seconds, which turns out, if you calculate, 317 years. Even if you sped it up to 1 billion, which is 1,000 million, it's still 116 days. Now, this is why cryptography works. There are just so many possibilities to look at that nobody has the time or the computing power to do it. I mean, the other way to think about this is that you might have 116 computers, each working for a day, to guess the credit card number or to guess a password. If you just put in an extra 3 digits, this goes back to 317 years at 1 billion guesses a second. Okay, stop sharing. Right. So let's meet tomorrow.